Okay, guys, very important. Your programming test 1 is coming. All right, not as soon, but in about 2 weeks' time, including this week. So your programming test 1 guide will be released most likely tomorrow. I'm just finalizing some details and make sure the other 2 colleagues also agree for other sections. So there will be also some example question released also for you. So if you got any questions, they should be already answered in the guide that you will see most likely early tomorrow, I would say, by lunchtime, around that time. Okay, and then I can speak briefly about it, some highlights, maybe on Thursday class. All right, split array harder. I've been talking about it. That one solution has been released, both the Java code and also tutorial video. Take your pick, which one might be useful to you. For those of you who might be struggling, still understanding recursion in general, so I would suggest the video. I recorded fresh for you guys, so you can definitely take a look. I think it's going to be helpful. Let me know if you got any issues there, understanding the split array harder. And then for your assignment number 2, don't need to mention, require and recommended study. I mentioned that last time, right? So just make sure you catch up with the studies. And assignment number 1, if you still got any question about it, let me know as well. And lecture note templates, office hour, TA contact, all consistent, right? It's always there. Any questions about the course? All right, let's now do some very quick recap. And then we'll move on to continuing the syncly linked list. All right. So last time, we actually revisited this exercise over here, especially we talked about a precondition formulated in predicate logic, right? That's really the highlight for this example here. So you can take a look, right? Everything's there. And then we spoke about how you're supposed to construct a chain of nodes using different approaches, right? We talk about if you simply want to go for this version here, it's simply not going to work because it wouldn't compile, right? That's an easy programming question to answer. And then we spoke about if you want to construct the nodes, let's say the nodes themselves, just setting the next to be null, and also set the next accordingly in a separate lines. That's also fine. If you find this approach more straightforward, feel free to use it actually in your programming test and also the assignment. No problem at all, which one you choose. And then in order for you to really create another level of object here, syncly linked list, you just got to set a head, right? That's also something we talk about. And we talk about the empty syncly linked list. Basically, you got only one attribute here. So if you got only, if you have no nodes in the list just yet, so the head will just be pointing to null. As opposed to if the list itself is just pointing to null, like here, it's a different category of objects, right? Just make sure you distinguish between them. It's very important, okay? When we get to the doubly linked list, hopefully later today or Thursday, I will come back to some similar visualization to help you, okay? We'll come back there, go back there later. And that's the first algorithm we talk about on syncly linked list, how we can count the number of nodes. You can look at all the details, especially tracing. I think it is very important. And think about the current over here is a very common pattern for traversing the list from the left to the right, from the head all the way to the rightmost node in the chain. It's more like a loop counter for linked list. And then we spoke about how you can find the tail of the list. This one's similar pattern, except that we also keep another reference to the node. Now, in your assignments or in your programming test, you might be expected to somehow keep track of the list by multiple pointers. So that's something you have to practice when you're doing the assignment. So depending on the problem, sometimes maybe one single reference might be okay. Sometimes 2, sometimes 3, you got to judge. And we talk about the principle of trading the space for time. Basically, we're just saying you can introduce more attributes to the syncly linked list class. In this case, we have tail, we have size. After we have introduced these 2 attributes here, the good thing is every time we want to know about the size or the tail, we can simply just do attribute access, which we know is constant time. On the other hand, you want to make sure all the subsequent implementation for the methods, you have to update these 3 attributes appropriately. For example, if somehow you forgot to update and the size suddenly become 2, you can see 2 is inconsistent with the fact that we got 3 nodes, something like that, right? So for all the remaining algorithm we're going to talk about today on syncly linked list, we have to make sure we update the tail and the size and also the head properly, right? So that's something you want to also pay attention to. Whether you want to really trade the space for time is your choice as a developer. But for now, we assume we're trading space for time by introducing these 2 additional attributes to the syncly linked list class. All right, so that's the last example we talked about last time, just about adding the first node, right? I wouldn't dive much into it. Just think about how you can trace it. And just by looking at the code without understanding the logic, you can see it's only if conditional. There's no loop. So it should be a constant time operation. Very efficient. On the other hand, if you want to insert, let's say you got an array, something like that, right? Everything has been filled out already. If I want to insert at first, what should I do? I should somehow grow the array and copy everything and leave this guy here for the first, right? So that's going to be a linear time operation, as we said earlier. Inserting or removing for the array is going to be very expensive, linear time, right? You want to do the contrast with the array. All right, any question? All right, so one thing I would like to share very quickly with you, that was an insight brought up by one of your fellow students in the evening session last Thursday. So I just want to be fair. I want to mention this nice little addition about third approach to build a chain of nodes. All right, so I'll just talk about it very quickly in the beginning. Alrighty, let's say this is the chain of nodes that we want to build, and we want to set it to be the head, right? Like that. Let's say that's what we want to build. So that's what we give it. Let's say we give it a singly linked list called list, right? We're just creating that. Maybe in the beginning, it's simply head is just pointing to null, let's say, after this line. And can you write just a single line of code in Java to build this chain of nodes right here and set a head at the same time? That's the challenge. Because in the previous approach number 1, approach 2, we had to do multiple lines, at least 3 lines. Right? That's a kind of minimum in approach number 1. But now I just want one single line. Can it be done? All right, for those of you who say yes, okay, I'm going to dive directly to the solution. I'm pretty sure you learned about something called anonymous objects, right? Like objects without any name. So this will be something you will have to take advantage of. So here I'm doing the example on the linear collection here. In the case of trees that we're going to see in assignment number 3 and 4, you can use a similar approach, anonymous object, which I'll revisit again to show to you. All right, so to really solve this problem here, we have to use something called anonymous object. Objects without any name. Anonymous objects, right? So here we are supposed to create a chain of nodes, 1, 2, and 3, 3 objects. All the 3 objects are going to be created on the fly without any name. All right, and of course we're going to set the first node to be the head. So what we're going to write will be something like this. We already got a list. And we know that we have a method called setHead. All right, let's start with that. Before, we can simply pass, for example, just Alan right here. But we're not doing that. We want everything to be done in a single line. Okay? So to make it a little bit more structure for you, why don't we say, the first node I'm going to create, I'll make it blue. All right? Blue is fine. And the second one I want to create, it will be green. And the third one I want to create will be pink. All right? In this order. Okay, let's now deal with the first node, which is going to be set to be the head. So what I will do is I'm going to say new node. And I know that the node constructor is going to take Alan, right, as an element name. Alan. And then remember the next argument is going to take another node reference here, right? But I don't want to create any reference for that. I don't want a name. I'm going to say another new node. And that new node is going to be Mark right here. All right? That one there is going to be new node right here. And then I'm going to say Mark. And after Mark, I should also get another node here. But I don't want to pass just Tom reference. I want it to be anonymous object as well, to remain in the same line. So here I can say new node. And this will be the end of the chain. So I can say new node and then Tom. And then now I can say null. And I can now close the parenthesis. You got to be very careful when you write this, because if you got the parentheses are matched, you're going to write into compilation error, right? So you can see here, I'm just closing the pink one over here, and then I'm going to close the green one right here. And then I'm going to close the blue one right here. And then finally, I'm going to close this initial set head parenthesis. Oh, that's not a color. There we go. And then semicolon. All right, that's the single line. All right, any question about this? All right, that's something I would expect you guys to know. All right, that's a simple one, but very handy. Here, it's a very nice way to see a linear collection. You can think about Alan here got its next node right here. And this node got its next node right here. And this one got its next node pointing to null. Exactly a linear collection. Later on, we're going to see that when we got a non-linear collection, how can we build it in this similar manner? That's something a little bit more advanced, but just slight extension. That's something we'll see later. Okay, once you got assignment number 3, I'll show to you how you can do that. All right, that's a very nice insight brought up by your fellow student last Thursday. So I thought it's good to share. All right, so if you go back to the slides, I think we already finished discussing insertFirst. That'll be slide number 21. Okay. By the way, I also make some update to the slides. If you want to re-download the slide, feel free. And also some notes template. You can also download them. Okay. So the example zip code is already on the lecture slide. I showed it to you last time, right? All the sample code is there. And all the exercises I kind of ask you to complete in the slides, you should also put the extension over there. Okay, I'll leave you to that. The first exercise is very easy. You basically just compare these two test cases just to see how the nodes are being constructed, right? That one's very easy. Use the debugger if you can just practice using the debugger to see how things are being constructed. Okay, this second exercise here is more interesting. I want you to add 2 methods into the singly linked list class. One will be removeFirst, the other one will be addLast. But I'm going to give you some visual hints before I let you, do it. All right, let's now talk about the hints and sketch a little bit, which is pretty much what you got to do for the assignments and also programming tests. Whenever you're given a new problem on a singly linked list, you always have to somehow sketch a little bit and think about what will be the boundary cases, like for example, list size is equal to 0, or maybe the list size is equal to 1. So these are the typical edge cases that we're going to consider. And also, what about the general cases where we don't have to worry about like a specific, like edge cases, right? So let's say removeFirst right here. So removeFirst means we want to somehow remove this node here from the list. And then, of course, you have to somehow, the head must be updated. It should not be pointing to here anymore. And the tail may have to change, maybe. It depends. Okay, I'll talk about it. And also the size must be changed as well. So you can see now we're assuming that we got a head, size, and tail, trading space for time. So all these 3 attributes may have to be impacted by this method here. You got to make sure you update them properly. All right. So these 3 attributes over here have to be updated consistently. Updated consistently. That would be the job of your implementation. All right, let's talk about different cases, right? If you want to remove the very first node, you got to think about different special cases, right? I'll get right to it. What if the size of the current list is 0, empty? Can you remove anything from empty list? No. So this will be like an exceptional case. You had to throw some kind of exception, which you learned from 2030, right? I'm going to sketch the idea with you. So for boundary case number 1, if the size of the list is simply equal to 0, in that way, you have to throw kind of like exception. You can throw illegal argument exception. It's already there in Java library, or you can just create your own exception. It's up to you, okay? Unless you're otherwise kind of specify what to do. And for removeFirst, there's another special case that's interesting. Because we are removing, right? So if you're removing, what if the current size is actually equal to 1? That means after there's only 1 node for you to remove. That's already the first node. If you remove it, the list is going to become empty. In which case, the head and tail are both going to point to null, right? So that's something you got to watch out as well. All right. So second special case would be if the current size is equal to 1, right? So the resulting list will be empty. So the result will just be empty list. Okay, I'm just going to visualize it a little bit for you, and then you got to work out exactly what to write. Okay, so if you got a singly linked list object here, right? SLL, and we know that we got 3 attributes right there, right? So we got the size. Okay, sorry, a little bit small here. I'll make it a little bit larger. So you got the size, you got the head, you got the tail, right? So now size should be set back to 0. And both the head and the tail should be set to null. Agree? Right? Because that's the only node you can remove, right? Easy case, but you gotta make sure it's there. And I'll give you a little bit preview, okay, which I may be able to get to either today or Thursday. This kind of edge cases handling is correct. However, as a good software engineering principle, if you can keep your code as simple as possible by not having to deal with edge cases, it will be the most ideal. So now in the case of doubly linked list, which we're going to talk about, by a simple extension at a list level, we will be able to avoid having to consider edge cases. Right? So just take that for granted for now, and I'm going to show it to you either today, maybe not today, possibly on Thursday. Right? We'll get there. All right, so these are the 2 edge cases you want to consider, and then let's talk about a more general case, right? So equal to 0, equal to 1. Okay. What about general case? It cannot be 0, cannot be 1, so the size must be at least 2. That means the size must be larger than or equal to 2, right? Logically, that makes sense. And let's take this one as an example, right? If you want to remove first, what will be the step? So I'm not going to give you any Java code here, right? So that's something you really want to practice, translating from the arrow in the diagram into the corresponding Java code. That's really something you want to do, okay? So step number 1, we might need some temporary variable. So I can just say here, this is something called temp, or whatever you like. This will be step number 1. Right? You know what to do. And this temp should really be pointing to the existing head or the old head, which is going to be removed pretty soon. And then we want to make sure after this, eventually this node will be removed. That means the head, rather than pointing to here, it should really be pointing to this particular node, the second node, right? Currently the second node. So step number 2 will be, rather than pointing to here, it's now going to point to right here. That is step number 2. All right, step number 2 you got to do. And step number 3, you want to make sure this node here should be completely detached from the chain of nodes. So you better set this next here to be null as well, right? So this part over here, you want to set it to null. I'll just say 3. All right, number 3. And also, don't forget, you have to update the size. Currently, it should be 3. I forgot to put it. Currently, it should be 3. But after you remove the first, it should not become 2. Currently, it should be 3. And then after you remove it, it should be 2. All right, should be 2. And this will be step number 4. All right, so you're going to somehow put steps 1, 2, 3, and 4 together. All right, that's a hint for you. Or you can think about this as kind of the sketching process you want to have whenever you're trying to solve an algorithm. You don't necessarily have to write a code right away. Find some representative example there on the paper and try to sketch out the visual solution and then translate it into code. That might be easier, right, as a beginner, or even for advanced algorithm. All right, any question about the first method here? We're good? All right. Second one, we want to, let's say, add a node to the list. We want to add last. So currently, we got 1, 2, and 3. We got 3 nodes. What we want to do is create a new node and then somehow add it. So the existing tail should now point to that particular node. And also, we should also reset the tail to be that particular node, and etc. Right? That's what's involved. Of course, you also got to update the size. Right? Let me remember this time. At the moment, the size is 3. It should be updated as well. That's really the trading for space, trading the space for time catch. You want to make sure you update all these 3 attributes whenever necessary. All right, so let's talk about boundary case. right? So it turns out there's only one boundary case over here. Remember before we actually got a boundary case when the size is equal to 1, right? Size is equal to 1 for removeFirst is a boundary case, but it's not a boundary case for addLast. Because if you already got one node in the chain, well, adding another node as a last doesn't really make a huge difference compared with other cases. So the only special case you will need is this one here. You can think about why, right? For different algorithms, there's boundary cases might be different. So we only need one, right? So here we say size is equal to 0, right? If right now the list is just empty, after adding to the last, we just got one node. And that node should be the head and the tail at the same time, right? So what we'll do is, let's say we start with, visually, we start with this singly linked list right here. We got a head, we got a tail, we got a size, right? All these three. To begin with, we got the size being 0. That means the head and also tail are simply both pointing to null. What we want to do is we want to add a new node as a last node, right? And then the node should be pointing to some data elements of string E, right? Whatever E is. So let's now create a new node right here, right? If we create a node, right? Notice that it's a different type. It's a node. And then it has the element, it has the next right here, right? And that's the only node. So the next will be pointing to null. And the element will be whatever E is pointing to, right? Aliasing. Right? That's the node itself. After adding this as a last node, it's really just like adding a first node. It doesn't make a difference, right? Because there's only one node afterwards. So what's going to happen is head is going to point to that node, and the tail is also going to point to that node. And size will be incremented from 0 to 1. So you can see all the three attributes must be updated in this special case. Right? Try to see if you can translate this kind of visual solution in Java. Should not be too bad, right? Of course, that should be under a single if conditional when size is equal to 0. All right, that's the first one. Okay, let's talk about general cases. So general case will be when the size is at least 1, not empty. So general case will be when the size is larger than or equal to 1, right? So that's a general case that we are dealing with, okay? All right, let's see what we can do. Let's say for this list over here, it's already size 3. If we want to add a new node, basically the node is going to be right here, and then somehow we're going to do something here. All right, let's say exactly the steps. All right, let's say step number 0. You got to create a node first, okay? So step 0, we're going to just create a new node that's going to be added. So it's going to be a node with elements and also the next. Okay, right here. We got the elements, we got the next. And that should be null. And the element should be pointing to wherever E is pointing to, right? Some string. Step number 0, okay? Create a node. And step number 1. What used to be the tail should now become the second last node in the chain. That means this next over here, rather than pointing to null, is now going to point to this new node. Agree? All right. So that'll be step number 1. Rather than pointing to here, it's now going to point to right here. Step number 1. All right, and the next step will be, let's now reset the tail. The tail, rather than pointing to here, is now going to point to this particular node. All right, this will be step 2. All right. And a final step will be, you got to update the size from 3 to 4. So that'll be step number 3. So in total, you're going to need 4 steps. So 0, 1, and 2, and then 3. Let's talk about the runtime very quickly. You can see that we don't even have a Java code, but we can already analyze the runtime, right? Like how we did it for selection and sort. and insertion sort. What about remove first? Right here, right? Basically, there's no loop. So the algorithm does not depend on how many nodes you have in the chain, right? So in that way, it's going to be big O of 1. Okay, because the algorithm does not depend on the size of the chain of nodes. If it does, that means you need some loop to really go from the left to the right, right? But it's not the case. So it's going to be big O of 1. Very efficient operation. Similar logic can be applied to addLast. Here, you just need a tail reference, which we have. That one's a constant operation, right? Also, this one here will be big O of 1, right? For the similar idea. All right. All right, any question about these two operations conceptually? We're good? All right. And then you just got to make sure you kind of understand this and then being able to sketch them visually, diagrammatically, and translate the corresponding arrows, boxes into Java code, which should not be too hard, right? And this part here may be very, is the most important step because if you got this, this kind of stage right, the rest can just be correct very straightforwardly. Okay. All right, if no further question, let's move on. Okay. And here is one question for you to think, right? We don't need to discuss the answer just yet. We have addLast right here. We want to add the string. Okay, let me highlight it. So this is the method that we just discussed, constant time operation. What about we want to remove the last? It turns out remove last is a fundamentally different operation compared with addLast, given that it's a singly linked list. If you know why, keep it to yourself. You don't know exactly why, wait. We're going to see that, right? But you just got to remember, addLast and remove last in the context of singly linked lists are two very fundamentally different operations, asymptotically, right? We're going to talk about it. All right, so let's now talk about the next algorithm. Let's say we want to access, we just want to get some node. We don't want to modify anything, right? We just want to get the node somewhere in the middle. It could be in the middle position, or it could be maybe about 1/4 of the position, in etc., right? So we're going to make some parameter. So this algorithm here is going to take one parameter called I, integer I, right? I could be, for example, 0 if you actually want to get a first node. It could be the size -1 if you want to get a last node, and etc., right? So you should really know what the input constraint is. So what we'll do is, let's now take a look at if I got any. Okay, so this is the input assumption. I, the smallest value will just be 0. The largest value for I will be list.getSize -1. Right? That'll be the last node that you want to get. And let's take a look at what's going to happen here. All right. All right, so we're talking about getNodeAt right here. And then this is the I that we are given. All right. And let me just remind you once more. It is very important. All right. So let's say input assumption. So for I right here, okay, 0 less than or equal to I, you can say less than or equal to list.size -1. Like that. All right, that's the important assumption you should really know. And that one there is also very important for us to figure out how many iterations we're going to need and also what's the worst case. But we'll do that a little bit later. Let's focus more on the logic right now, on the code. So here, the first one here, always think about what might be the exceptional scenario. Because whenever you're taking some input from the caller, they might give you something that's simply not possible. For example, let's say here we got the size being 1, 2, and 3. And they say, I want to get node at 3. Not possible, because we got indices 0, 1, and 2 only. We don't have 3. So if you got any input like that, you should really give them some exception. So that's exactly what this one is saying, right? If the I is either too small or too large, in that case, you should really get some error, like an exception, okay? So that's something you definitely should do. And then this will be the part where we try to get the normal scenario executed. Okay, so we got two variables here. Okay, let me get right to it. Index right here, and also the node here. To some extent, the index over here is very similar to the size variable that we spoke about earlier when we want to count the number of nodes in the list, except that now we don't necessarily have to go all the way to the end of the chain. We don't have to. If the I value happen to be somewhere in the middle, in that way you can exit the loop when you get to that middle point. You don't have to go all the way to the right most point always. Right? That's some subtle difference, but we still try to trace the code. So what we'll do is, let's now see what's going to happen, right? So now in the beginning, we got index and we got current. And let's see how they're going to change, okay? So at the moment, the size should be 3, right? By the way, the size, the head and tail, they are not going to change at all because we just want to get access to the node. We don't want to change anything. So the question here, you want to ask yourself, does it change anything? No. Okay, we can answer here right away. We don't need to worry about that for this particular method. So what we'll do, let's see here. Okay, so after these two lines, we're basically going to get index and current. Right? Let's trace them. So the index that we eventually that we're going to use initially is 0, and then the current is going to point to wherever the head is pointing to. Right? You can see the head is right now pointing to this node. So this will be the current right here. All right. And one thing to also note here, you can see that we got a while loop here, and the condition here is index should be less than I. You should really think to yourself, when does the loop exit? Right? That's also a very important point to think about, right? It should be as soon as this particular less than is negated, is evaluated to false. Should be when the index is exactly equal to I, right? Exit when index is exactly equal to I. That's also very important for you to understand the logic, all right? So here we're not really using to say, for example, current.next equals to now, or current equals now as the exit condition. It doesn't need to be. Right? So you just gotta get used to different possibility. And you can see every time we are trying to execute a loop, we're just going to increment the index and also move the current to the next node. Right? Every time. That's what we're doing. All right? Let's now see what's going to happen. At the moment, current is pointing to Alan. The index is just 0. All right? And then if we try to evaluate this condition here, it's going to be 0 less than 2. True. Of course, we're going to execute the first iteration, which is good. Right? And then once we start the first iteration, I'm going to write it here. Let's see what's going to change. For the very first iteration, we're going to change two things, index and the current. Right? Let's do that, and then I'll annotate the diagram as well. So the index is going to be currently 0, and also the current right now is Alan, right? It's going to be changed to something else. Index plus plus, right? 0 to 1. And the current, if I say current equals current.next, it will be Mark. Right? From 0 to 1 and from Alan to Mark, right? Diagrammatically, it's going to go like this. So 0 will be updated to 1, incremented to 1. And the current right here is now going to move to right here. Another annotation that might be useful for you to see. Conceptually, think about what we're having is, we got index 0, index 1, index 2. Remember when I talked about relative positioning, right? So the indices for linked lists also start, conceptually, also start with 0. Okay? So I can also put, think about index 0, index 1, index 2. All right? So you can see at the moment, we got the current pointing to the first node. and the index is exactly 1. So they're in sync somehow, right? Let's now try to see if we need a second iteration. So the current node is actually mark. And the index value is 1. So we're going to evaluate this condition here for the second time. So 1 less than 2, true. Second iteration. So when we do the second, okay, let me write a little bit better. When we do the second iteration, so we're going to say index currently 1, and also the current, which is pointing to mark. They are going to be changed. All right, so let's see. Let me change the color here. So let's now use red, let's say. So index plus plus right here, and current equals current.next. 1 to 2. And current, rather than pointing to here, is now going to point to the next node. Right? So that means it's going to go from 1 to 2, and also it's going from Mark to Tom. Right? That's basically what's going to be done for the second iteration. It seems like we're almost done. All right? Oh, by the way, I forgot to mention. When we trace this method here, you got to give a concrete value for I. I assume it's 2. Okay, sorry, I forgot to mention. Right? It's 2. So this 2 here is just the I that we are tracing. All right? And then we're just going to see one more. So currently we got, let's say we check this condition here for the third time. So current is now Tom. And index is actually equal to 2. And when we check this, 2 less than 2, false. No more third iteration. Exit from the loop. All right. Any questions so far? We're good? All right. If you're okay with it, let me just mention one more time. When you study this example here, you really want to make sure you try to observe the relation between the index value and also the current value. In the beginning, index is 0, current is pointing to here. So whatever index is storing indicates where the current is pointing to, index 0, and etc. Right? That's something you want to watch out for. And also, let's now talk about the runtime. Right? We really got to figure out exactly how many iterations. Well, I got 2 iterations at this point. Right? So let's see here. So that's what we have right here. So right here. So we got 2 rows over here corresponding to 2 iterations. And not surprisingly, if you look at the 2 over here, first iteration, second iteration, they correspond to just the value of I, depending on which I you want to get to. If you want to get to the index I being 2, in that case, you need 2 iterations to get there. Because even before the first iteration, you're already here. The first iteration brings you to here, second iteration brings you to here, and etc. Right? So the number of iterations you will need will be corresponding to the value of I. Okay, first of all. So here, the number of iteration equals just I. And we learned earlier, I would be less than or equal to size minus 1, n minus 1. And for each iteration, we know that, for each iteration, it's just primitive operation, constant, right? So what I'll do is I'm going to put here, big O of, I know the worst case will be n minus 1. That'll be the largest value I can have for I. Multiplied by 7 and 8, these 2 lines are all constant. So 1 here is about line number 7, line number 8. n minus 1 here is the maximum value for I. Right? That tells you what that's the maximum number of iterations you're going to run. But if you simplify that, just linear. All right? Obviously. Drop all the lower 10, drop all the multiplicative constant, that's what you will get. So this is not a cheap operation if you want to get it somewhere in the middle. You might get some extreme cases. Let's say if I happen to be 0, in which case you can get ahead. If I happen to be, let's say, n minus 1, you can get a tail. That's okay, sure. But if your I is equal to maybe n minus 2, n minus 3, you still need a linear operation. Right? So that's something you want to watch out for. Any question here? Okay, good. Okay, another one, another comment I can make. Maybe there's a potential confusion. Okay, I'll put it here, right here. When I is equal to n minus 1. In that way, maybe you can just say list.tell. Sure, that may not be the worst case, you may argue. I would tend to agree, which is big O of 1. However, when I is equal to n minus 2, let's say, right? In that case, there's no way for you to say tell, I want to go to the previous node right away. There's no previous reference for syncly linked list. In that way, you got to be big O of basically minus 2, right? That one's still got to be big O of n. Still the same. All right, any follow-up to this example here? It should be still straightforward, but it's a very fundamental operation. Later on, when we try to do a little bit more, slightly more advanced operation, then we might need this as a helper method. So we're going to assume you know how this method works. Alrighty, let's now move on. All right. So now we're done with accessing the middle. And if you think about what's going to be the corresponding operation cost for the array. For example, for array, if I want to access to the middle of the array, constant time, just indexing, right? So you can see that's another example where what's really expensive for the linked list, in this case, is going to be cheap for the array. Okay. All right, so I think, yeah, exactly here, right? Accessing an array element will just be constant time operation, right here. Okay. Let's talk about one more. Okay, let's see. Okay, good. The next one, let's see how we can insert into the middle. If you want to insert into the middle, apparently you're going to modify the chain. At least the size has to be changed, incremented by 1. So this is something you got to make sure you also update consistently. Okay. And I want to insert a new element at index I. Again, we got index I again. So we are following the same convention. But now the assumption will be a little bit different. If you say I want to insert at index 0, that's like addFirst, which we spoke about already. So you can simply invoke addFirst as a helper method. You can also say insert when I is equal to exactly the size of the input list. When size is equal to n, this will not be a valid index. But if you pass n as the I value here, that simply means you want to add as a last node to the list. All right? That's something I'll also show to you. I just want to mention first. All right, so you want to watch out for this assumption here, right? If you compare this assumption here about I versus the assumption on I for accessing the middle, like what we just did, it's slightly different. The main difference is right here, right? You can see I may be equal to the size of the list. That means you want to add the new node as the last node, basically. All right, just keep it that in mind. And let's not worry too much about the special case. Let's look at the general case first. All right, right here. The special case will be when I is exactly equal to 0. But let's say I is already larger. Okay, let me put it here, just in case you're confused. Okay. The case where I is equal to 0 is discussed separately. Consider separately. How about that? Consider separately. And to be more precise, you can simply say addFirst. And then E. All right, that's an important subtle difference to note. Right? Let's say we want to insert into the middle, and we're given I. Now, it's very important to notice this. We are only given some integer here for I. All right, so I'll put it here. Only an index is given. That means in order for us to do all the arrows changes, let's say, for example, this is the node that's at index I. In order to actually insert a new node in the same index, it turns out we might need the reference to the previous node. But I'm going to show to you. But to really get this previous node reference, we cannot really get it from the input parameter because it's just an integer. So what we need is we need to somehow call the getNodeAt as a helper method that we just discussed as a helper method, right? That's kind of the flow I'm going to show to you. Okay, it's given. And then let me just say a little bit more. Okay, I'll put a star here. I'm just running out of space. So you're going to say another thing will be reference to the node at the previous one. Since we want to insert at I, we want to know what's the previous node at I minus 1. At index I minus 1 is not given as the input to the algorithm. If it is not given, but it's necessary, we got to calculate it ourselves, which is going to be costly, it turns out. All right, so this point here is very, very crucial about the I. I itself is an integer. It does not really give you the direct reference about the previous node at index I minus 1. All right, so let's now take a look. Okay. Let's now take a look at exactly the visualization. Let's say this is a chain of nodes somehow, right? So now we got index I, so we are only given this I. This is the method parameter. Method input. That's what we're given. That's it. And we are also given the element that's to be stored in the new node, which is also very useful, of course, but we're going to see how to use it. All right? Let's now discuss the steps that will be involved. Right? You can see the E here is already pointing to some string. Right? We're going to use it. Okay? Step number 1. We're going to create a new node. That will be the easy part. So we're going to create, let's say, a new node right here. Okay, there's a new node we're going to create. And we got the elements, and also we got the next. The elements can just point to, sorry, let me change that a bit. Okay, you can just point to wherever E is pointing to, right? Right here. That one's easy to set. But the next, let me just put null, just for now. Okay, that's how we create a node first. So this will be step number 1. You want to create the new node, and you know the Java syntax for that. And then somehow we want to say, this is I minus 1. After the insertion, this remains to be index I minus 1. This one here that we want to insert into should be index I. And this one that used to be index I should now be I plus 1. Agree? All right. So this one here, you can think about remains after insertion. And this one here, after insertion, is going to be index I. And after insertion, is going to be I plus 1. It's a bit like a shifted by 1 position to the right, right? The right by 1 position. All right, once this kind of understood, so now we can see exactly how the arrow should go. Ultimately, we want to make sure this I minus 1 position here, the node, rather than pointing to next here, it should point to here. And the next of this, rather than pointing to now, it should really point to here. That's what we're going to do. But the problem is, we don't really have this node. So we should really get it. How do we get it? We're going to call the getNodeAt I-1. So this is the critical part for this algorithm here, right? So again, let me recap. For this algorithm here, you're only given the index I, integer. But to really complete the operation, you have to know the reference for the node at index I-1. For that one, you need to call the helper method. All right? So let's now do that. So now to really get this reference over here, let me call that previous. So you're going to say previous will be assigned to getNodeAt. And it will be I-1. This will be the second step after the new node creation. And just by the way, you might be thinking, oh, would it be useful if I also call getNodeAt I? It turns out no, not at all. I'll put it down and then tell you that you don't need to do that. All right? If you actually try to say, I want to also calculate maybe getNodeAt I. Okay, this one, it turns out, is useless for this algorithm. Just not necessary. All right, so after step number 2, we can now refer to previous. All right, what we should do is now for step number, for the next step. All right, for the next step, we can simply try to, let's say, let me use the maybe pink. So now you can see this one here, rather than, oh, sorry, step number 3. We want to make sure, you got to make sure the sequence is followed, right? The next right here, rather than pointing to null, is now going to point to right here. This will be step number 3. This would be something like, let's say this node that we are creating is called n, the new node. You can simply say n.next is assigned to the previous .next right here. Okay, I'm writing this down because that one's slightly more sophisticated, so it's okay to write it down right away. All right, that's step number 3. And then we can now try to do another one. We want to make sure we set this one here, right? Right here. So now we can try to do, let's say, purple here. So this one here, rather than pointing to right here, is now going to point to here. All right? So that one will be step number 4. Which will be the previous next is assigned to n, the new node. So after this, what we have is this particular structure. Right here, index I-1, point to index I, and then it points to index I+1, and then it continues onwards. That's how we insert in the middle at index I. All right. And one more thing to say. You want to really pay more attention to this particular step, step number 4. This particular step. Okay? This step here is really important. This step here really requires the node to the previous node, the reference to the previous node. Requires the reference to the node at index I-1, right? If you don't really have the previous node, there's no way you can complete this algorithm. So that's why you really need this helper method call in step number 2. All right, any question about this one? This is just conceptual sketch, and we're going to see the code as well. Okay, we got 3 steps in total. Okay. Okay, 1 here, 2 here, and 3 here. That will be it. Okay, good. If you're okay with it, and let's see, we're going to see some Java code, I believe. Okay, let's see. Let's trace this one very quickly, and then we'll take a very short break. Okay. All right, so this one here, let's see the test case. Okay. You can also look at the test case in the source code. It's a test singly linkless addAt. Okay. For this part here, you can easily check it's a empty singly linked list to start with. And then we spoke about how you can trace the at first last time. So after these lines over here, after these, you will get exactly this structure here, Alan, Mark, and Tom. Right? For that one, we don't need to repeat the tracing. And what I want to do is, let's talk about, let's say, these two. Right? We want to add at. Okay? The first one, the value is 0. And the second one, the value for I will be 2. All right? Let's see both of them. The first one. Let's say we want to add at index 0. That one there basically is going to reach this particular base case, right? Well, I shouldn't say base case, I mean edge case, right? You can see when I is equal to 0, it will be as if we just add first. And you know how the add first should be executed, right? You can refer to the coding from last time, all right? So for this one here, pretty easy. So when we get 0 here, we are just going to first create a new node over here, add first. So that will be a new node. So elements and also next. And we say Suyang over here. So element will be pointing to Suyang over here. And at first, you can trace the detail, but after that, the next is actually going to point to right here. And the head is not going to be here anymore. It's now going to point to this new node, right? And the tail doesn't change. Agree? Okay. So after this, you're going to get the head pointing to this new node, and the new node points to the old head. Okay, nothing else. That's the first one, right? Special case. You can see at first is going to be called, which we know how it works. The interesting case will be in the general case. Let's say we try to add at index 2. And think to yourself, if I want to add at index 2, which node reference do I need? Index 1, I minus 1. Remember in the conceptual sketch, right? You can make a note right away. We will need the reference to the node at index 2 minus 1, right? It's going to be at 1, right? When you calculate the I minus 1. Let's now take a look how this one is going to be executed. So when we got 2 here, it's not going to satisfy the edge case condition, so we're going to go to the else part, right? So this is where the general case is going to execute, this part here, the general case. Not surprisingly, we're going to calculate something called nodeBefore, all right? And then we're going to get nodeAt I minus 1. You can see the I right now is actually 2. So we're going to get 2 minus 1, which is going to be 1. So we also learned about how to trace the getNodeAt, right? Let me get right to the point. So think about what's happening here. So if you think about 0, 1, and 2 right here, in order to add at 2, we're going to get getNodeAt 1, which is exactly this node right here, right? So that one there is going to give us back nodeBefore. All right, let me just make a little bit more notes for you. Okay, so this will be the getNodeAt 2 minus 1. All right, index 1. And then the next line, the new node that we're going to create is going to be whatever E is. In this case, it's going to be UNA. And then we're going to also set the next node at the same time. Right? You also know that syntax from before. And the next node right here is going to be the nodeBefore dot next. Basically, I'm going to insert in between, right? That's why. Okay, I'm going to kind of do two things at the same time. Okay, so what I will do is, first of all, I'm going to create UNA here. Let's say here we got the node. And this one here is going to be called a new node. Okay, I'll go a little bit slowly here. So here we got elements, and also we got the next. The element is going to be UNA, as we can see there. All right, this part here, you want to watch out. Okay, this part here, you can see the next reference for the new node is going to be node before, which we already got, .getNext. So node before .getNext is going to give you this node. All right, I'll also make a note here. So this one here is the node before .getNext. And this one here is going to be set as the next node for the new node. All right. And if you like, I can also number them, right? Think about here, we got 1 here. Oh, sorry. We got 1 here, we got 2 here, we got 3 here, and we got 4 here, right? 1, 2, 3, 4. Number 1 was done right here. Get a previous node. Number 2 was done right here by creating a new node and set the next reference, right? 2-step in a single one. And the step number 3, node before .set next. Node before .next should no longer be this one here anymore, right? So we're going to set this one, the next should be the new node right here, right? That'll be step number 3. So step number 3 would be this one here, rather than this, is now going to point to this new node right here. Okay, I will do some highlight very soon. And then finally, you got a size plus. So right now the size, well, after what used to be 1, 2, and 3. So used to be 1, 2, and 3. So that one I forgot. 3. After adding this one here, you will go from 3 to 4, right? Also, after adding this one here, you go from 4 to 5. Right? That will be basically step number 4. So after this, you can see that what we get is from the node before, we get to here. And from that one there, we get to right here. Right? Like that. Any question about this? Yeah?
So like let's say we're adding to the last element of the node, where would I update the tail of the code?
You definitely have to update the tail as well. Let's see here. Absolutely. Because, we don't need to update the tail in this case. Because you can see that we are basically inserting, after this one still remain to be the last node. So we don't need to update the tail. If we had to add the end, so you may want to add that special case. That's something you may have to judge as well. Yes, good consideration. Yes, absolutely. So what your fellow student was saying is very important. So when you revisit this code here, think about, does it really consider the case where if you are adding to the very last node right here, right? In that case, have we properly also set the tail to be this new node? Right? Think about that case too. Right? Yeah? Yeah, you can add some special case, yeah, for sure. But I would say here I'm just discussing a general case. You want to add another edge case to make it a little bit more efficient, feel free. Yeah, it's open source already to you, so you can think about how you can modify that. All right, so let's. Any questions before we take a very short break? All good? All right. Why don't we take a very short break and then take attendance? All right, so we are done with this one here, inserting to the middle. You can definitely go back there and revisit. Okay, it's going to help. All right, so what about the array? If you want to insert into the middle for the array, it's also going to be linear. So you may not feel too bad about using simply linked list for this particular case. But you just got to be aware about which operation might be more expensive for one data structure or the other. Right? All right. Let's talk about another one, right? Removing from the end. Remember the little question I kind of spoke about, something you want to think about, right? So we talk about addLast, but let's say remove last. They're going to be very different operation, right? If you want to add a last, all you got to do is you want to set the tail next reference to that particular new node. That's what we spoke about. But if you want to remove the last, this is tricky. It may not be as simple as you might think. All right? Let's say, for example, Okay, I'll get to the code right away, but before that, right? Let's say this is the list I got, right? If I want to add last, create this node here. I already got the tail reference. I can set its next to here. Easy, constant. But if I want to remove the last, here's the problem. I already got a tail reference over here. I agree. Is it going to help me to remove the last? Not really. Because in order for me to remove the last, I need to somehow get rid of this node by setting the previous node, like a second last node's next, to be null. But the problem is I don't really have this reference. So I need to compute it myself. If I want to get to the second last node in the list, it's going to be about n-2 iterations I need to traverse there. In that way, it's going to be big O of n. So that single step of just getting to the previous node, previous to the last node, is going to be linear time operation. Okay, it's a very quick sketch just to give you some intuition about addLast and removeLast are fundamentally very different. They're simply, well, in the case of the simply linked list. All right. So what we'll do is we're just going to look at the code. You can look at the code on the slides, but I'm just going to trace one case together with you. I think that'll be enough. Okay. Again, you can look at this particular test case, removeLast, right? So the setup will just be the same. After a series of add first, we got this structure, Alan, Mark, and Tom, the same. Okay. We just want to trace one single line, removeLast right here. That's all we want to do. Okay, how exactly do we do it? Okay, and of course for other like edge cases, you can definitely give it a try. Let's say you tried, you already got the list being empty, where you want to remove last. That should really give you some exception, right? Things like that. But that's something you can try. So when you actually execute this line here, I know that the size currently is actually 3, right? Of course, I should have drawn also the tail and also the size, right? They should be there. Okay, let me just do that quickly. Oops. Okay, right here. I got a tail, I got a size. Apparently, this would be, sorry. Let me do it again. Yeah, this would be the tail. And the size currently is actually 3. Right, that'll be complete. How do I do that? If I say I want to remove last, I'm going to trace this code. Size equal to 0 equals to 1. They're both going to be evaluated false because size is equal to 3. So this one here, not really. This one here, not really. All right? I'm not going to execute those lines. So I'm going to do this line here. This branch, what I meant. Let's now number them and see exactly what's going to happen. Let's say here, 1, 2, 3, and then 4. Okay, 4 steps. Let's see exactly what's going to happen. Step number 1. We're going to get a second last node, obviously, right? So it's going to be size minus 2. That one there, when you try to calculate getNodeAt, this one here is going to be big O of size will be n minus 2. I know that many iterations will be necessary. That one there is already giving me linear time. So this algorithm is destined to be linear time, right? We can realize that right away. And second last node, right now, the size is actually 3. 3 minus 2 is going to be 1, right? 3 minus 2. That means, let's see here, we got 0 here, 1 here, and 2 here, right? So that's going to give us 1. So second last node is going to point to index 1, right here. Second last node, right? That would be step number 1. All right, step number 2, we are going to set the second last node next to be null, because it's not going to become a new tail pretty soon. So second last node next, rather than pointing to here, is going to be null right here. That is step number 2. All right. And then step number 3, we're going to update the tail right here. Tail is going to be the second last node, obviously, right? So rather than pointing to here, the tail should be pointing to where the second last node is pointing to. This will be step number 3. All right, pretty much done, but don't forget, you also got to decrement the size since we're removing. 3 down to 2. All right, you can see this algorithm here, once you know how this particular helper method is working, it's not bad. You just have to realize to really remove the last, you cannot just use the tail reference. You have to know where the previous node is. That's a critical thing. And to really calculate a previous node, big O of n. Okay? It's going to be the dominating step. So overall, if you think about the remove last, it's going to be big O of n. Because it's already dominated by this step right here. Okay? All right, any question about this one here? Very good. All right. This one here. Okay, let me talk a little bit more. Okay. So once we're done with it, we're pretty much done with singly linked list. I think what's left will be another 2 exercises. I'll give you some hints, and then the next one we just to have a table to compare. Let's see how much we can do for the remaining time. We'll see. All right, how about we do at least sketching some exercises for you so you can also do something before Thursday. Okay. All right, so the exercise will be, let's now consider 2 more methods that are kind of interesting to implement. Okay. You can also refer to the slides. I already also give you some textual hints, but I'm going to discuss them also on the iPad here too. Okay, let's now talk about them. They're kind of symmetric, kind of. I want to insert after. Oh, sorry. So one method is called insert after. The other one is called insert before. So both methods will be just void method. They do not return anything. Okay? They are definitely going to modify the chain of nodes structure. Okay? But now this time we are lucky because we are given somehow the node reference rather than just I. But you still got to judge whether given this particular node reference, is it sufficient to be efficient? But we're going to see. All right? Let's say here, when I say insert after node n and string e, node n is already pointing to somewhere in the middle in general. Okay? So what I want to do is I want to insert after this particular node some new node. That's what I want to do. All right? Let's see how efficient it can be, whether there's any additional calculation we might need. Right? Let's now talk about this. Okay? So what I can do is, let's say, okay, apparently there is one node here that's going to be the next node. So think about this one here is really n dot next, right? Right here. That's an important node. Of course, n dot next may be null. If n is already the last node in the chain, it's possible, right? Let's say here, and then what we got to do is, first of all, we got to create a new node. That's the first step. Let's now create a new node right here. Okay, just watch out the time. Let's create a new node. And we got elements and also we got next, right? Elements and also next. Element is going to point to this one here. And the next, it should really pointing to right here. Eventually, and the next for the n should really point to here. That's insert after, right? But let's do that in the right order. The first step, of course, will be to create a new node. And the second step, we should really set the next of n to this new node right here. And next will be just to the new node. All right, that'll be the second step. And the third step will be, we want to make sure we set the next right here to this one here, right? That one is easy because we can just say n dot next. So that one there is going to be, let's see here. So this will be the third step. So we can say the new node next should be assigned to n dot next. All right, and step number 4, you should also make sure you kind of detach this one here, right? So step number 4, And next should be set to null. Right, so these are the 4 steps. So after this, this is what you will get. So the original end is here, but we insert some node after that. And that node that we inserted should really point to wherever this node used to point to. Right? It's not there anymore. So that's insert after. Does it look cheap to you, like efficient? Yeah. Right? I don't need to calculate any additional node, especially the previous node. That's good. That one there is going to be just big O of 1. Just about different operation to set the arrows, to set the references, which is good. And then we're going to look at this one here. If I want to insert before, hopefully you can already see. If I want to insert a node before this, let's say there is already a node that's before this node. I only know the reference to this, but I don't know the reference to this. I need to compute that, basically, so that I can insert a new node in between. All right, so that's what I need. Let's see if how much I can do. So let's say this one here. This will be the previous node. So this will be basically the previous node. I need to compute that. And also, I need to create a new node right here, and then set a reference accordingly. There will be a critical step about how this can be computed. I will leave that detail maybe for next time. All right, so before Thursday, you want to really start reviewing all the syncly linked list lecture we have covered. We are almost to the end. After these 2 examples here, we're going to talk about some table to compare syncly linked list very quickly, and then we'll move on to doubly linked list. All right, see you on Thursday.